This is the final section of organic reactions, and we will discuss the reactions by aldehyde, ketone, carboxylic acid, and its derivative. So let's start with carbonyl compounds. In the alcohol section, we have learned that by oxidation, the primary alcohol will become aldehyde first and then become carboxylic acid. In the view of redox reaction, the reaction will run in the opposite direction for the reduction. Similarly, the secondary alcohol will be oxidized to ketone, and the reduction will change ketone back to the secondary alcohol. Here, we use acidified potassium dichromate as oxidizing agent. So, is there any suitable reducing agent? In DSE, we have two choices. The first one is sodium bromohydride, NaBH4. It is a mild reducing agent in aqueous solution and hence suitable for secondary students for the safety purpose. However, it is not strong enough to reduce carboxylic acid. The second one is lithium aluminum hydride, LiAlH4. It is the most powerful reducing agent in DSE, which is strong enough to turn carboxylic acid back to the alcohol. And it is too reactive and unstable towards water. That's why it should be used in an anhydrous environment, for example in dry ether. And all the unused reducing agent should be removed immediately after the reaction. That's why students should include two steps in your answer. The first one is lithium aluminum hydride in dry ether, and the second one is acid. For the reaction of carboxylic acid, first, we should recall that it is an organic weak acid. That means all acid reaction you have ever learned in the acid and base section is valid. For example, acid react with metal to form salt and hydrogen. Let's recall that only metal with reactivity higher than copper can form hydrogen here. And this is one of the reactions. The second one is neutralization, where acid react with base to form salt and water only. Again, even lower acid react with sodium hydroxide is a typical example. But this reaction is far more useful than preparing salt. It provides a good practice in separating carboxylic acid from the mixture with other organic compounds, which we will have further discussion in the later section. The third reaction is reacting with carbonate or hydrogen carbonate ion. Among all functional groups in organic chemistry, only carboxylic acid is strong enough to give carbon dioxide with carbonate or hydrogen carbonate ion. This becomes a signature chemical test for carboxylic acid, and here shows some example equations. Next one is reduction. As we have mentioned in a few minutes before, only lithium aluminum hydride can reduce carboxylic acid to primary alcohol. And don't forget, two steps should be included in your answer like this. Next one is esterification or formation of ester. Ester is formed when carboxylic acid react with alcohol with the elimination of water. Concentrated sulfuric acid is needed as catalyst and dehydrating agent. Also, reflux is necessary. The reaction is reversible, and that's why a double arrow is shown in the equation. In examination, ester is always described as fruity or sweety or pleasant smell. All these terms indicate the existence of ester. The final one is the production of amide. There are two possible methods. The first one is the carboxylic acid neutralized by ammonia, then heat the ammonium salt. This method is simple as only ammonia is used, but the yield is low. The other method is let the carboxylic acid react with PCl3 in the first step, then react with ammonia. This method may be more complicated as more chemical is evolved, but the yield is much higher. In examination, both methods are acceptable, but I recommend the second one personally. As you know, both ester and amide can be prepared from the carboxylic acid, so the chemists call them carboxylic acid derivative. Now, let's see how they decompose to give out the carboxylic acid. For ester, which is formed by reacting the alcohol and carboxylic acid, the decomposition is just in opposite direction, as water is needed in the process. This is also called hydrolysis. In normal condition, the hydrolysis undergoes in a very slow pace. That's why we need acid or alkali to speed up the process. In acid hydrolysis, as the reaction is reversible, which means the product can react with each other to form the reactant again. As the result, both reactant and product will exist no matter how long the reaction goes, and this reduces the reaction yield, which is not favored to the industrial process. On the other way, the alkaline hydrolysis is a one-way reaction because carboxylic acid formed during the hydrolysis is neutralized and cannot become reactant again. That's why we have 100% yield in this reaction. But the problem is we only get carboxylate ion now. So what should be done if we want to have the carboxylic acid? The answer is simple. Just add strong acid to the carboxylate ion. Being a weak acid, the anion will absorb the hydrogen ion quickly and become molecule again, and the carboxylic acid can be obtained. Amine have similar story as ester, but this time the carboxylic acid and ammonia will be formed after hydrolysis. And the problem is these two products have opposite behavior. One of them is acid while the other one is base. That means we cannot obtain both products at the same time. In acid hydrolysis, the ammonia will be neutralized and become ammonium ion, and here shows an example. While in alkaline hydrolysis, the carboxylic acid will be neutralized to form carboxylate ion. Again, a strong acid can be used to regenerate the carboxylic acid molecule again. And that's the end of this section.